In certain confidence interval questions, you're going to be asked to find what size sample do we need to get a desired margin of error. That's what this video is going to focus on. Sample size questions are derived from the equation from their confidence interval. So for example, categorical data, we would use this equation up top, p hat plus minus z-score times that standard error. And the margin of error is from the second part of that equation. So we're adding and subtracting the margin of error from the point estimate p hat. If it's quantitative data, we have the same thing. We have our point estimate x bar, add and subtract this margin of error. So here's the part of the equation that we'll be using for sample size questions. Let's start with a question about categorical data. In preparing a report on the economy, we need to estimate the proportion of businesses that plan to hire additional employees in the next 60 days. How many randomly selected employees must we contact in order to create an estimate in which we are 90% confident with a margin of error within 4%? So we have this equation here. Now we could just plug everything into this equation. The only thing that's going to be missing is the n. Now I say the only thing that's missing is the n. It actually doesn't give us anything for a p hat. And when we don't know what that is, we're just going to put in 0.5 for the p hat and the q hat. Right? Sometimes it'll say a previous study showed a sample statistic of p hat equals like 0.3. Okay, then we can plug that in for p hat. What I like to do is I like to rearrange this at the start. So I want to get this n by itself. So to start, I want to move this c to the other side. So I'm going to divide by z, divide by z. All right, so now I have this. Margin of error divided by that critical z-score equals that standard error. To get the n by itself, I'm going to square both sides. And now I have this equation, at which point I can cross multiply. Get the n off the bottom. So n times the margin of error equals the z-score times p hat q hat. And lastly, divide by margin of error. Same thing over here. And we get the equation with just n equals. That's what we're going to plug into. Now, if you can get to this point, you're going to get the question right, because now it's just plugging in values to our equation. It had mentioned we want to do a 90% confidence interval, so we're going to put in a z-score for 90%, which is 1.645, 0.5 for p hat and q hat, since it's unknown, and we want a margin of error within 4%. Make sure you put this in as a decimal, 0.04. Plug it all in, we get 422.8, and we would always round this number up regardless of what it is, unless it's a whole number. Okay, so we get 423 as our desired sample size. Now to illustrate a key point about sample size problems, let's redo the same problem, but instead of doing a margin of error within 4%, we're going to change it to a margin of error within 2%. So here's what we had just done. We got a sample size of 423. Now we want to change that margin of error from 4% to 2%. We get 1691.2. Even though this is closer to 1691, we always round it up, so our sample size is 1692. Now, the thing that I want you guys to take notice of is that if we took this 423 and we multiplied it by 4, okay, it's going to equal exactly what we got over here, 1692. So the reason for this, the justification, is that we started with some sample size, n. Okay? If we make that sample size 4 times as big, how would that affect our margin of error? Well, think back to your radical rules from algebra and algebra 2. We have a 4 inside this radical. We can move it to the outside, and it's going to become a 2. All right? It's going to stay where it is in the fraction. It's on the bottom. It's going to be on the bottom and the outside. So this 4 moves from the inside to the outside. Square root of 4 is a 2. Our margin of error just got cut in half. So the margin of error is affected by the square root of the sample size. So if we wanted to cut the margin of error to 1%, okay, from the original 4%, okay, we would have to do a sample size 16 times as big, right? Reason being that the square root of 16 equals 4. That would put a 4 on the bottom of our fraction. The margin of error would get cut in half. I'm sorry, cut into fourths. Okay, so it's always affected by the square root of whatever the scale of our sample size is. With quantitative problems, the equation's a little easier, but sometimes there's an additional step. Here we have a medical researcher that collects body temperatures from 52 adults. They find a mean of 98.285. standard deviation of 0.6824. How large a sample would we need in order to estimate the mean body temperature to within 0.1 degrees with 98% confidence? From that confidence interval equation, this is our margin of error portion of it. Now, the issue is that when we're dealing with quantitative data and we don't know the standard deviation of the population, this is the standard deviation from those 52 adults, we have to use a t-score instead of a z-score. The issue is that a t-score is based on degrees of freedom for which we need a sample size, and we're solving for a sample size. We don't know what n was. So for that reason, the only thing that we can use for a critical score for 98% is a z-score. We're going to do that first. So we're going to use a z-score for 98%, plug everything else in, and we have this setup. So now the only thing that's missing is the n. Normally I would rearrange this equation before we plug it in, but if you like to plug it right in, we're going to do it that way for this problem. So we want to divide both sides by this 2.33. Move that to the other side, moving everything away from the n. This point we need to get this n out of the square root. So let's square both sides. We have this. Cross multiply to move the n up to the top, and divide by 0.1 squared. All right, so here's our equation. We get 252.8, and we're always going to round this up. Now, this is not our answer because we're not supposed to use a z-score here. We're supposed to use a t-score. Okay, so now we can use this sample size to get an approximate critical t-score and redo our problem to get a more accurate value. So what I mean is now we have an n, and this n is going to be relatively close to where we end up. So we can use this to get a degrees of freedom, 252. Now we look up a critical t-score using that degrees of freedom for 98% confidence. We get something that's close to 2.33. Okay, instead we're using 2.34. Keep in mind, if we had a small sample, this could be different substantially. We redo our problem just like we did before, and we get a new sample size. This time it's 254.98. We round it up. The sample size we want is 255. Sometimes there's a shortcut and a critical z-score is enough. For example, our original problem said this medical researcher collected body temperatures from 52 adults, found a mean of 98.285, standard deviation of 0.6824. These are both about the sample of 52 adults. Let's say the problem changed, where instead of that, it started the same way. Medical research collects body temperatures from 52 adults, find a mean of 98.285, period. The standard deviation of the population is known to be 0.6824. That's telling us that sigma is 0.6824, and when we know sigma, we can use a z-score. And last sample size problem, sometimes it'll give you an interval, and we can find the sample size from that interval. Here it's giving us a 95% confidence interval for the proportion of babies that begin to crawl earlier than 9 months of age. We get this interval, 0.292 to 0.318. Now, we can find the actual sample statistic, the point estimate, from this interval, and it's just the midpoint of these two boundaries. So take this, add it together, cut it in half. 0.305 is exactly in between those two. So that's what the sample showed in however many babies or families they surveyed. Okay, we can also get the margin of error. Just take either of these. So I took the higher one, and now I subtract the point estimate. So in other words, this plus some number, which is the margin of error, would give us 0.318. 0.305 minus that same number would give us that. Okay, so if we find the distance from the middle to either of those boundaries, we get the margin of error 0.013. Once we have that, we can fill everything in. We know the margin of error. We know the z-score because it's 95%. We have a point estimate that we could use for P and Q, and the only thing that's missing is the n.